Hey everybody, I wanted to take a few minutes and introduce today the Chapter 9 for you since we had to miss the workshop due to system malfunctions. Chapter 9 is all about estimation. So in the course so far, we have been working with calculating things and trying to calculate probabilities based on some statistics and so forth. This module brings us into what's called inferential statistics, where we're going to be using a sample in order to try and predict a population value. So it is in three parts. You have 9.1, 9.2, and 9.3. 9.1 has to do with proportions, and we're going to start with that. 9.2 has to do with means, and we're going to go on to that. And then 9.3 has what methods should I choose, and you have to choose between the formulas and the methods for each one. So this is a typical example of a proportions problem. It says a survey of 2306 adults in a certain large county, age 18 and older, conducted by a reputable polling organization, found that 428 have donated blood in the past 2 years. So if I am thinking about this sample, this 2306 is the number of adults that they put in the sample. So here n would be equal to 2306. Now, age 18, this number 18 is not something that's used in the problem. It's a descriptor, but a lot of times there are numbers in the problem that are not necessary for calculation, and you have to be able to pick those out. The other number that we need is this 428. So these are the number of people who have done the thing of interest. So sometimes, depending on the author, this is either listed as an X or an R, but we have X here equal to 428. In both cases, whether they use X or R, it means the same thing, the number of people or things that satisfy your problem of interest. So if we're looking at a point estimate is a value from the sample that we're using to try and find a population value. So in order to calculate a point estimate, it's called p hat, and it's equal to x over n. And 428 divided by 2306. Oops. 428 over 2306 gives me 0.1856. Make sure you watch how many decimal places you need. So 0.186 to 3 decimal places. So as far as what we are required to have for a confidence interval, the lesson in the software will step you through all of the requirements. So we require that the sample is a simple random sample, and we're going to calculate that p hat times 1 minus p hat has to be greater than 10. So, and then at least the population has to be less than or equal to, or the sample has to be less than or equal to 5% of the population. So as you go through, these are the rules that allow us to construct the interval. Now we use a sample in order to estimate where the population proportion is going to be, and every time we do that, we do it with a level of confidence. So this one asks us to find a 90% confidence interval for the population proportion of adults who have donated blood in the last 2 years. So we are going to calculate that confidence interval. Now there are two ways to do this. There is a calculator method and there is a table method. And if you're using your calculator method, in order to calculate it, you would use stat and then tests. Once you hit tests, the one we're looking for is a 1 proportion z interval. So 1 proportion Z interval. Later on we'll use some of the other ones. If you select this option, it asks you for your value of x, it asks you for your value of n, and it asks you for the confidence level. So for this problem, I would put in the one proportion, Z interval, and then my x value is 428, my n value is 2306, and my confidence level is 0.9 or 90%. And then when I press that, what happens is it gives me the confidence interval. Now the confidence interval is going to be based on a proportion, so it does not actually give you values. You're not expecting something like 312 to 682. It gives it to you in proportion. So what you're going to get is a decimal, and if I calculate that really quickly, the decimals that it gives me are 0.17229 to 0.19892. Fix that up. If I'm rounding to 3 decimal places, then it would round to 0.172 to 0.199. So somewhere between 17 and almost 20% of the population will have donated blood in the last 2 years. Now, if you're doing this by hand, the first thing that we have to get is a z-score that goes with this level of confidence, or this 90% confidence level. Now, the hand calculation is based on tables, and it's based on a formula. So this is the formula sheet that you're going to get for the final exam. And here we're calculating a confidence interval for P. So we're going to calculate a margin of error that's based on this term here. And here I'm looking for our margin of error is going to be a value of z that we're going to pull from the table times the square root of p hat times 1 minus p hat all over n. Now we actually have most of those values already because we already found p hat. In order to find the z-score, I pulled my z-table off of the e-learning course because that's the one that you'll have for the final exam. Looks exactly the same as the one on my stat lab, with one exception. There are some values here at the bottom that are used for confidence intervals for levels of confidence. So if I'm looking for a 90% level of confidence here, then my critical value, my ZC that I use, is 1.645. So going to this calculation, I have 1.645 times the square root of p hat, or 0.18. I'm going to keep 4 decimal places. 1 minus p hat all over n. Now anytime you're calculating a margin of error for a proportion, it should be small. So 1.645 times the square root of 0.1856, 1 minus 0.1856, all divided by 2306, and I get 0.10133 to 4 decimal places. Now constructing the actual interval, if we go back to our formula sheet, once you have found the margin of error, we're going to take p hat and we're going to subtract the margin of error to get the lower limit or lower bound, and we're going to add the margin of error to get the upper limit or upper bound. So going forward, that means that our confidence interval is constructed like this. We have 0.186 minus 0.0133 and 0.186 plus 0.0133. So if we do that arithmetic, 0.186 minus 0.0133 gives me 0.1727 to 4 decimal places, and 0.186 plus 0.0133 gives me 0.1993. Now you notice that the difference, there is a little bit of a difference based on the calculator method and the table method, and that's okay. It's based on rounding. So we're rounding intermediately on this side, but not on this side. The calculation's all at once. My stat lab will take it both ways. When we do a test, it will also be okay both ways. So which method you use is up to you. All right, other calculations for proportions in this are going to be based on sample sizes. So if we want to estimate the percentage of adults who support abolishing the penny, what sample size should be obtained if we wish to be within 3 percentage points, or 0.03, with a 99% confidence. And there are 2 different types of sample size calculations. Your formula sheet has the formula for both. So if you have an estimate for the proportion, then the sample size is calculated like this. If you do not, then a sample size is calculated this way. So it says on this first part that we are going to use a previous estimate of 28%. So here we're going to use p equals 0.28. And then our sample size, n, is equal to p times 1 minus p times zc over e squared. Be careful that you square this last term because that is probably the most common mistake, is not squaring it. So we want to be at the 99% confidence interval. So going back to my z table, confidence interval of 99% means that I need a ZC of 2.575. So for part A, n is equal to p is 0.28 times 1 minus 0.28 times ZC, or 2.575, over E squared. Plugging that into my calculator, gives me 1485.26, and we always round up to the next integer, so here I would use 1486. Now if I don't have any prior estimates, then the only difference between the two is instead of using p times 1 minus p at the beginning, I'm going to replace that beginning term with a fourth. So 1/4 times ZC over E squared. Now these are problems that have to do with proportions of the population. We also have some that have to do with means. So what I wanted to do before we branch into those is talk about the t-table first. So the t-table is listed here, and it's based on area in the right tail. So you have an area in the right tail, and it's based on a degree of freedom. So if I pull up that table, this here is the area in the right tail. So if it says it has 0.1 in the right tail, that's how you pick your column. So this here has 0.1 in the right tail. Degrees of freedom are in this first column on the left. So if I'm looking for an area of 0.1 and 10 degrees of freedom, then where those two intersect is the value of t. Now the reason that we use this t-table is for means typically, and it will be used for our confidence intervals as well as hypothesis testing a little later on. So here, this is area in the right tail of 0.1 with 10 degrees of freedom. Remember right tail, oh, it's 0.01. Be careful on decimal points. So area in the right tail means that this value is going to be positive. So t would be equal to, let's go back and get 0.01 instead of 0.1. So 0.01 instead of 0.1, 2.764 for our value of t. Now if my area is in the right tail is 0.2 with 29 degrees of freedom, same thing. So that's how you should be looking that up. Find a t-value such that the area to the left of the t-value is 0.25 with 20 degrees of freedom. Well, the t-distribution is very similar to the z-distribution in that it's symmetric. So if I have a value here with 25% or 0.25 of the area, this would be a positive value of t that I get from the table. Using symmetry, there's also a negative value on the opposite side that has 25% of the area to its left. So this would be a negative value of t, but those are still the same value of t. So 0.25 with 25 degrees of freedom. 0.25 here, 25 degrees of freedom, gives me 0.0684. That's this one, 684. The one over here is negative 0.684. Now the last one is the one that we're going to use for this section, and it says find the critical t-value that corresponds to 95% confidence. Unlike the z-table, you don't have this nice use these for confidence intervals. Although there is another t-table on e-learning that will give you some confidence, some two-tailed values of t. This one that's on my stat lab does not. So if you are looking here, confidence intervals are based on the area in the center. So that means that this part here in the center is 95%. If I'm looking for a value of t, then that means that over here and over here together are 5%, or 2.5% in each side. So we call this alpha over 2 because it's the area over 2. And if I put 0.05 divided by 2, then I get 0.025 for the area in each side. And I'm going to look up that 0.025 and 13 degrees of freedom from my table. So 0.025 here, 13 degrees of freedom gives me 2.160 for my confidence interval. All right, last thing. I'm only going to do part of this problem, but if we are going through and trying to find a confidence interval for a mean value, anytime you're dealing with a sample mean, then you are going to be working with the t-distribution instead of the z-distribution. So x bar is our point estimate. And what we are going to add and subtract from. Here we have the sample standard deviation S, and it gives us S is 10. So the values I have are x bar of 112, S equal to 10, and then it says to construct a 90% confidence interval if the sample size is 23. So n is equal to 23. And the reason that 90% is important is if I go to the formula sheet, when we're calculating confidence intervals for the means, this is the margin of error that we're going to use. So we need a t-value from the table, and then we're going to use s and the square root of n. So our margin of error is our t from the table times s over the square root of n. And then we'll take that value and subtract it and add it to x bar to get our lower and upper bound. So confidence interval, if I have 90% in the middle, this here is 0.9, then that means I have 0.1 left, and for each side, each side is going to be half of that, or 0.05. So let's take that information and bring it to the t-table and find our value of t. All right, so 0.05 is our column, and our n value is 23. N helps us find our value of t because our degrees of freedom is equal to n minus 1. So when I go to the table, I'm looking for 22 degrees of freedom, and I get 1.717. So degrees of freedom is equal to 23 minus 1, or 22. Continuing for our confidence interval, E is equal to TC, 1.717, times S, which is 10, divided by the square root of n, which is 23. Putting that in my calculator, 1.717 times 10 over the square root of 23 gives me 3.5802. Now our mean is 112. They want us to round to one decimal place when we're done, but our mean is 112. So our confidence interval is going to be constructed as x bar minus e and x bar plus e. We're going to take the mean and add and subtract our margin of error. So the mean is 112 minus 3.5802, and 112 plus 3.5802 gives us our answer. Rounding to one decimal place, I have 108.4 and 115.6. All right, feel free to reach out to me if you have any questions, and I hope you have a great day.